Alright, so welcome back to the video on circular motion. So now we're going to be moving on to example number 1. So the hard drive in a certain computer stores data on a thin magnetic platter that spins at high speed. The platter makes one complete revolution in 0.00833 seconds. So here we're going to determine the frequency in both hertz and revolutions per minute. So we have two different calculations here to look at. So first what we can look for is we can first look for our hertz, just because we have our units here are in seconds, and then we can convert our answer afterwards to revolutions per minute. So just to start, so we can talk about the frequency, or calculating the frequency. And so this one here is the equation's given by its units. So we know that hertz is equal to cycles per second. So here we know that it's one complete revolution or one complete cycle, and it took 0.00833 of a second to do that. And so if we plug into our calculators, we should go 1 divided by 0.00833, and you'll get a fairly long number in your calculator, but we're just going to go ahead and we're just going to jump straight to just answering with sig figs. So we should have an answer of 120 hertz for our frequency. We have 3 sig figs here. We have an 8, a 3, and a 3, which makes a total of 3 sig figs. So our answer needs to have 3 sig figs as well. So we can put a bar over the 0, or you can even write it in scientific notation. So that there is our frequency. The answer here also wanted it in terms of revolutions per minute. And so, as I mentioned in the previous video, we could look at using a method of unit analysis to complete this, or you could just multiply and divide by 60. So if you're not sure which one you should do, then what I would recommend is write out your frequency in terms of, and break down the unit of hertz. So that should be cycles over seconds. So it should be 120 cycles, which I'm just going to put as a C here, divided by seconds. And we want to change this to revolutions per minute, or that would also be cycles per minute. So I want to change the seconds into minutes. So I'm going to multiply this by a second fraction. So I'm trying to get rid of seconds, so I'm going to put the seconds in the top, and my minutes go here down on the bottom. And I know that there is 60 seconds in 1 minute. So when we see the 60 seconds up in the top, that means that we're actually going to take this 120 and multiply it by 60. So if we plug this into our calculator, if we go 120 times 60, we should get 7,200, with our third digit there being significant. Remember, we don't include 60 seconds because that's an actual value that we know is true, so we don't have to worry about the 60 being included for the sig figs. So, especially with a bigger number like this, it might be best to put it in terms of scientific notation. And it's a little bit more, it nicely kind of reflects the fact that there's 3 sig figs. So you take your first digit and then separate it with the second one using a decimal, and we're adding that 0, so we have the sig figs. Then it's times 10 to the power of, we want to move our decimal once, twice, 3 times. So we are to the power of 3. And our units here are RPMs. So then just to answer that question, we are going to write it as a sentence. So we could say the frequency of the platter is 120 hertz, or 7.20 times 10 to the 3 revolutions per minute. So there's a quick example on calculating your frequency and then converting your units to revolutions per minute. Alright, so now let's take a look at speed and circular motion. So at this moment, Earth is approximately traveling at 107,000 kilometers per hour in its orbit around the sun. So I think part of the question is, well, how do scientists know that we're traveling at approximately 107,000 kilometers per hour? And so when we're working with speed in terms of circular motion, we can actually use, we're going to technically start off with the formula for speed that we know from our first unit, which is V is equal to delta D over delta T. Now, one thing that's going to be really important about this part here is that, yes, we're technically be using a formula that works with our change in our distance over our change in our time. But first of all, when we're working with the change in our distance, when we're talking about circular motion, we're looking at the distance traveled going around in a circle. So really, we're looking at the circumference of the circle. And then remember, when we're working with our time in terms of circular motion, we're looking at how long it takes to complete one full cycle or one full circle. So this one here, we would actually be looking at our period. So we're going to come up with a brand new equation for our to calculate speed for circular motion on the next page here. So I'm just going to scroll down. All right. So as I had mentioned just seconds before, in the case of circular motion, when we're working with distance, this is the distance around a circle, so that is your circumference. And we can denote that with a capital C. So your circumference, if you guys remember back to grade 9 math, that is 2 pi r. If you're given your radius, and there was a different equation if you're given your diameter, but typically in our cases here, we're just going to be working with our radius. So we can actually substitute in that this distance around the circle for our delta D in our equation. So we have speed is equal to 2 pi r, which is our distance traveled over the change in time. So then next, as I had really talked about, when we're talking about circular motion, we really only want to talk about what is the time taken for one cycle. So we're actually going to replace our delta T with our period variable. So it's 2 pi r divided by our period. And so this is one of the formulas that is actually on your formula sheet. So if you guys are trying to keep track, you guys can put a little check mark beside this one, and now we know it. So let's go back to that Earth example where we talked about it traveling approximately 107,000 kilometers per hour. Okay, so if the Earth has an orbital radius of approximately 1.50 times 10 to the 8 kilometers, and it makes one complete revolution in 365.25 days, we can determine the speed. And so in this example here that we'll just quickly complete, we are going to first work with meters per second in terms of a speed, and then I'll also show you, just as a recap, how to convert to kilometers per hour. It's been a little while since we've done some of those conversions, so we're first going to work with meters per second. That is a very common unit that we use in physics, and most of your questions are going to be working with meters per second. But I will show you how to work with kilometers per hour, especially because we're working with big units. You typically, for those kind of big questions, you will want to work with kilometers per hour. But we'll go through each of those different steps. All right. So first, before we even jump into any calculations, let's first identify what we're given. So here we're told that we have an orbital radius of approximately 1.50 times 10 to the 8 kilometers. So 1.50 times 10 to the 8 kilometers. So as I said, we're going to work with actually finding our speed in terms of meters per second. So I'm going to convert this kilometers to meters. And in order to convert kilometers to meters, you're going to times that value by 1,000, which will just, when you're in scientific notation, it'll add 3 to your exponent. So it adds the number of zeros there. So you have 1.50 times 10 to the power of 11 meters. So the next thing here that we're given here is we know that we have one complete revolution in 365.25 days. So what we really need to work with here is we need to have our period in terms of that speed equation for circular motion. So the period there is, in terms of, it's usually time in seconds divided by the one cycle. So it's how many seconds it takes for one cycle. So here we know we have 365.25 days is how long it takes to complete one cycle. So what we're going to do is we're going to convert this days into seconds. So once again, I am going to use unit analysis, so I'm going to create my fractions here. So if you know how many seconds are in a day, that is fantastic. But if you don't, then that's fine. Just work with a step-by-step conversion. So I know, say for example, that there is 24 hours in one day. So notice here that I put the day on the bottom here because I'm trying to have them in opposite places. So one's on the top, one's on the bottom, so the units cancel out. So if I were to complete this calculation, then I would be left with hours. But remember, I want seconds. So this one here might be a little bit more familiar, but hopefully from other examples, we know that there's 3,600 seconds in 1 hour. So here our units are going to cancel out. So what we'll be left with is cycles per second, or seconds per cycle, sorry. So I want you to go ahead and plug this onto your calculator. Notice how all of our values here are in the numerator or the top of your fraction, which means that we're just going to multiply all of this together. So if you plug that into your calculator, we get a ginormous number of 31,557,600 seconds per cycle. And one thing that we commonly do, just for short term and just kind of keep our units simplified, is we can even express our period in terms of just seconds. All right, so now we're ready to actually find the speed in terms of meters per second. Feels like a lot of work just to get to that point. And it was, I guess I will admit, it was more work because we did the conversions. If I just asked for kilometers per hour, it would eliminate half of all this work. Okay, so looking at our speed, that is equal to our circumference, or the distance you traveled, which is 2 pi r, divided by your period. So that is equal to 2 times pi times your radius, and we're going to use in terms of meters here. That's divided by your period here, which we had is 31,557,600. So go ahead and plug that into your calculator, and we should get a value of 29,865.32. And so before we're done finding our speed in terms of meters per second, we also do need to make sure we account for our sig figs. So that's really important here, is that we account for sig figs. And so here we can accept, we know that a year is approximately 365.25 days. I know this little 0.25 is a little bit, weird, but just remember there's a leap year every 4 years, so just to account for that difference. But yeah, so we just need to count our sig figs, and that is in terms of our distance. So here we had 3 sig figs in our value here. So our answer needs to have 3 sig figs, making our 8 significant. So our answer here is 29,000, and the 6 is going to round the 8 up to a 9. So you have 29,900. This one here is a bigger value. Typically if it's more than 100, I would write this in scientific notation. So our answer here should be 2.99 times 10 to the power of, we're moving it once, twice, 3 times, and 4. And our units here are meters per second. All right, so in order to convert to kilometers per hour, I'm actually going to do this in the next video because I'm just running out of time here. So we'll see you in the next video to finish up this question.